Okay, thank you everyone. It's a pleasure to be here. And so today I'm going to be talking about using deep reinforcement learning to attack blockchain incentive mechanisms. And this was joint work with a number of fantastic collaborators. So Charlie is my student at CMU, Mingxun is joining CMU next semester. Jan and Phil are our students. I think many of you know them. Florian is a student at Stanford, and of course, everyone knows Ari. So most blockchain mechanisms today use incentive mechanisms in some form. So the issue here is that to run a blockchain, you need to maintain consensus, and maintaining consensus can use a lot of resources. So that could be storage, computation, time, whatever. And to deal with this, we impose incentive mechanisms that reward users in the form of tokens for expending those resources. However, these incentive mechanisms can be susceptible to attacks, as we saw in the previous talk and in several of the previous talks. So I believe the first academic treatment of this subject was the selfish mining paper by Itai and Gun called Majority is Not Enough. And after that, there was a kind of an explosion of follow-up work on trying to analyze various types of attacks on incentive mechanisms in blockchains. And so we heard yesterday from Ari and Phil on front-running attacks in a new class. So how is this problem handled today? How do we deal with these attacks on incentive mechanisms? Well, one of the ways that people deal with this is to design new protocols and come up with new incentive mechanisms. So if we decide that there's a weakness in a particular mechanism, maybe we design a new one that at least intuitively should be robust, should be incentive compatible. And so these are just a selection of new blockchain protocols that have their own incentive mechanisms that are separate from Bitcoin's. And occasionally we see new theoretical analysis. So like in the previous talks, we saw some theoretical analysis. There's also been protocols like fruit chains, which had theoretical analysis associated with it, all in an effort to establish incentive compatibility. So is honest behavior a Nash equilibrium? So what's the problem with this approach? The problem is that doing this theoretical analysis is time consuming and requires expertise, and it just can't keep up with the rate at which new incentive protocols are popping up. So I think yesterday, Sarah Michael-John gave a talk that showed thousands and thousands of different blockchains. So a lot of them are using the same incentive protocols, but a lot of them are designing their own. And there's simply no way that all of them are going to have the relevant expertise to be able to do this kind of theoretical analysis and design incentive compatible protocols. So the goal of this talk today is to present SquiRL, which is a framework for automating the analysis of incentive mechanisms using deep reinforcement learning. So as part of this presentation, I'm going to talk you through some of the things that we can do with SquiRL, ranging from basic sanity checks, like recovering known optimal results for selfish mining under Bitcoin, to a number of case studies that illustrate, I think, interesting applications of this methodology. So the first case study we'll look at is trying to deal with a situation where we're looking at selfish mining, but agents can have stochastic hash power that's changing over time. A second case study is to identify a problem with the very commonly used rushing adversary, which is a model that we often use in cryptography and security to model a worst case adversary. And we found some kind of interesting and counterintuitive results in the multi-agent setting. The third case study is that we tried applying SquiRL to selfish mining with multiple competing agents. And we actually observed no benefit to selfish mining with 3 competing parties, which is kind of interesting and is at least consistent with the observation that we don't really see selfish mining in the wild. And finally, our fourth case study is to apply SquiRL to Casper, the friendly finality gadget. And we found a new attack that, that combines selfish mining with strategic voting in Casper FFG. So with that, I will start by giving just a little bit of background that we'll use to build on for all of these case studies that I mentioned. So for this crowd, I guess most of you already know this, but just to make sure we're all on the same page, in Bitcoin, the way that incentives are decided is split into block rewards and transaction rewards. So in this talk, we're going to focus entirely on block rewards, but a lot of the same ideas can be applied to transaction rewards as well. So in Bitcoin, whenever a miner mines a block, so let's say the blue guy mines the block, they get a reward that is associated with that block. And so here the incentive mechanism is trying to incentivize people to expend the energy required to mine blocks, which is substantial. So then if the red guy gets the next block, then he gets a reward, and so forth. And this block reward has been responsible in large part for the explosive growth of Bitcoin. So a lot of people invested in Bitcoin in an effort to accumulate these block rewards. And one of the key properties of the incentive mechanism in Bitcoin is that if a miner produces a block that's not on the longest chain, or rather the chain of greatest work, then that block does not accumulate any reward. So in this case, if the blue miner releases a blue block that's not on the longest chain, that block is not counted for a reward. So the blue node doesn't get any money for that. Now, what is selfish mining doing? Okay, so selfish mining is trying to increase the rewards of our red agent. And the idea here is that when the blue party, which we'll view as honest here, mines a block, he's going to publish his block immediately as per the protocol and collect his reward. However, when the red node mines a block, he's just going to hang on to it. He's not going to publish it immediately. So let's suppose that the red node mines 2 blocks in succession. And then finally, the blue node mines a block and publishes it again according to protocol. Now the red node is going to release both of his blocks to override the blue guy's chain. So what happens now? Now the red chain is actually longer. So the red guy gets 2 tokens of reward and the blue guy loses 1 of his. Okay. So by withholding his blocks and releasing them at a later point in time, the red node was able to amplify his own rewards with respect to the total rewards accumulated in the system. Okay, so this was the basic idea behind selfish mining. Now, a natural question, which is kind of the basis of this whole talk, is how do we figure out what are the best strategies for attacking this incentive mechanism? And to answer this, we need to first talk about the current state of the art, which is to model systems as Markov decision processes, or MDPs. So for those of you who are not familiar, an MDP is a model of an agent that is trying to maximize rewards in a randomized environment. So I think a good way to think about this, if you're not familiar with MDPs, is like video games. So if you have Super Mario who's making his way through the world, Super Mario has a few actions that he can take. Okay, so disclaimer, I've actually never played Super Mario, so maybe this wasn't a good example to go with. So I'm kind of winging it here. But let's say the Super Mario has a few actions that he can take. He can move forward, backward, like jump or squat, I don't know. And when he takes these actions, he can collect various rewards and impact his current state. So for example, if he decides to move forward, then his state in the world moves by 1 unit. But at the same time, his state can also be impacted by random events in the environment. So let's say Super Mario takes a step forward, but then a log falls out of the sky. Okay, so there are events in the environment that can affect your state, but also your own actions can affect your state. And the goal of this agent is to try to maximize their rewards. that are associated with whatever state you're in. So MDPs are a very old topic, and they can be solved exactly, asymptotically, with MDP solver algorithms. So two of the most common ones are policy iteration and value iteration. So for example, in prior work on optimal selfish mining strategies in Bitcoin, they used value iteration to solve an MDP associated with the Bitcoin selfish mining process. Okay, so what's the problem with this approach? Why can't we just model all of our incentive mechanisms as MDPs and then use MDP solvers to try to find optimal attack strategies? Well, the big problem here is that value iteration and policy iteration represent policies as matrices that grow in size with the state space and with the size of the action space. And both of these can actually be quite large in practice. So you can think of your state space as potentially being as large as the size of the entire blockchain or block DAG or whatever you're looking at. So these problems quickly grow intractable, and actually this problem is so, this is such a big problem that there are actually not results currently on optimal selfish mining strategies for Ethereum. Okay, so we've been able to solve it for Bitcoin, but in Ethereum, the state space grows too large. So there's really two main problems with value iteration, or rather posing problems as MDPs and then trying to solve them exactly. The first problem is that we cannot handle large or continuous state spaces. This solver algorithms just aren't made for that, and the convergence guarantees do not hold in those settings. And the second problem is that we cannot handle non-stationary settings. So in our example earlier with Super Mario, the only things that impact Mario's state is the actions that he takes and randomness in the environment. Now, if there's a second player in the game who's actively trying to screw Mario, then we have a problem. Then we can't represent this as probability transition matrices. And so this prevents classical techniques for solving MDPs from applying in this setting. Okay. So our idea here is to apply a different tool, which is deep reinforcement learning. So the idea here is that instead of learning this big matrix that I told you about, we're going to replace that gigantic matrix with a deep neural network. So here actually, let me try to use laser pointer here. Okay, so here on the left, we have a DNN, a deep neural network, that represents the mapping from states to policies. And this is going to tell us what action we want to take from a given state. So once our agent takes that action, the environment applies whatever randomized mechanism it is implemented to use. And then the agent collects some amount of rewards and observes the new state. Okay, so the real, I think, benefit here is, first of all, that we represent the value mapping as a DNN instead of a table. So that helps us deal with the exploding size of the state space. And the other benefit is that we don't require a full specification of state space transitions. And so this allows us to deal with non-stationary environments, for example, when you have multiple competing agents, like I mentioned on the last slide. Okay, so these are the two big benefits. So in this talk, I mentioned we have these 4 case studies that we're going to talk about, and each of them deals with one or actually both of these two problems. So our first case study on selfish mining with a variable hash rate is dealing with a situation where we have a non-stationary or an unknown environment. So MDP solvers cannot deal with that. The second case study on the rushing adversary will deal with a state space that's too large to represent. Third case study is again going to be a non-stationary environment because we're going to have multiple competing agents. And our fourth case study will implement a scenario where the state space is too large for MDP solvers. Okay. Okay. So let me start by describing our system. So with any system like this, there's a few components that you need to implement. First of all, we have the environment, and that has to be implemented even for MDPs. But also here we need to pick an RL algorithm. So in the case of an MDP, the RL algorithm would be policy or value iteration, like I mentioned earlier. But we said that policy and value iteration are not going to work for our purposes. So we're going to replace the RL algorithm, and we're also going to have to change the way the environment is specified. So for the RL algorithm, we used different algorithms for the single agent and the multi-agent setting. So for the single agent setting, we use something called Q-learning, which is a model-free algorithm that tries to learn a neural network for mapping states to policies. And this, for the multi-agent setting, we used policy gradient methods. And these are actually what's been used in some kind of high-profile deep reinforcement learning algorithms. Like if you've heard about OpenAI's algorithm that won the DOTA challenge, this was using a variant of policy gradients. And the other thing that we needed to change was the environment. So actually specifying the environment is kind of a complicated process that depends really on the consensus mechanism and the incentive mechanism that you're trying to evaluate. So I'll just give you a quick example for Bitcoin of what our environment looked like. And this is actually a simplification of what we really did just to make things super easy and simple. So for our state space, we stored two numbers. One is the length of the honest chain, and the other is the length of the agent's chain. And this is modeled, this actually looks identical to the optimal selfish mining paper that I talked about earlier. So if you're familiar with that paper, that's the environment model that we used for our initial experiments. Our action space is going to have 3 possible actions. So if you're a selfish miner, you can choose to publish your block, you can choose to adopt another party's chain, or you can choose to wait and continue mining. Our reward function here is going to be what's called relative reward. So the number of blocks mined by the agent over the number of total blocks in the longest chain in the case of Bitcoin. And finally, our probability transitions, our transitions from state to state are determined by random mining. So if you have 30% of the hash power, then with probability 0.3, you'll get the next block. Okay, and one thing that I want to really highlight here is that is our timing model. And this is a common assumption that's made in a lot of work on selfish mining, and also more generally in the cryptography and security literature. But we assume a rushing adversary, which means that our agent gets to see what the honest party is going to do before the agent makes their own move. So, so the way this works is in each time step, at the beginning of the time step, the environment is going to assign a block to one of our players. So let's say that it assigns a block to honest. So this is saying that the honest guy mined a block. And again, this happens with the honest guy gets it with probability proportional to his hash power. Now, if the honest guy mines a block, he immediately gets to choose which action he wants to take. And so the honest policy is to publish a block as soon as you mined it. So the honest miner is going to publish his block, and now the honest miner, let's see, hang on, sorry, let me try to get the laser pointer back. Okay, so now the honest miner perceives the tip of the longest chain to be the block that he just released. Now, upon seeing this, the agent gets to choose his action. So let's suppose that the agent in this case decides to adopt the honest chain, then the agent will also update its current view of the longest chain to be this block at the end. Okay. And we'll come back to this rushing adversary later when we talk about the second case study. Okay, so to start out with, I want to just show you our sanity check that I mentioned earlier. We would like for SquiRL to be able to recover baseline results, known optimal results from the Bitcoin literature. So to show this, we're going to compare to 3 baselines. One is honest mining, which is where you follow protocol. One is called SM1, which is the selfish mining strategy from the original selfish mining paper. The second strategy is OSM, which is the optimal selfish mining strategy, which was solved with an MDP solver. So that's the current state of the art. And here, what do we expect to see? We would like SquiRL to be able to come close to the optimal strategy. We know that it can't beat the optimal strategy because then the strategy wouldn't be optimal. But we would like to be able to at least come close. So here I'm showing you on the vertical axis, our relative reward. So that's a fraction, so it can be between 0 and 1. And on the horizontal axis, I'm showing you the attacker's hash power, alpha. And so here, this curve with the red stars, that's the honest reward. So if you're mining honestly, you should get a reward that's proportional to your hash power. And what we see here is that with the green crosses, this is SM1. So that gets a better reward than honest mining. And OSM, the optimal selfish mining, is these orange triangles, and that gets the best relative reward. And SquiRL, which is the blue circles, is achieving typically within a percentage point of the optimal strategy. And this highlights a really important point, I think, which is that with deep reinforcement learning, we can never say anything theoretical. Like if SquiRL suggests that a protocol is secure, it doesn't mean that the protocol is secure. SquiRL can only be used to find attacks in scenarios where we are not really able to use theoretical tools or like MDP solvers. Okay. So the point of this plot is to show that at least in this scenario where we know what the optimum is, SquiRL is able to recover it without too much parameter tuning. Okay, so let's move on to our case studies. So our first case study is on trying to understand selfish mining when our hash power is stochastic. So what does this mean? In the previous slides, in the previous sanity check, here we assumed that the attacker's hash power was fixed throughout the experiment. But in reality, an attacker's hash power might be changing over time. And in this case, it's not clear how to use these MDP techniques. So in particular, this is an example of an unknown environment. So it's not going to be possible to solve this with MDP and value iteration. So one natural baseline that we could try to use here is at each time instant. So let's say at time t1, I have this hash power here. I'll use the OSM strategy associated with that hash power. Then at time t2, my hash power increases to a higher fraction. Then I'll use a different OSM strategy, the one associated with the higher hash power. So at each time instant, I'm going to change my strategy based on my current hash power. So it seems like a pretty natural baseline, and I would expect this to do pretty well. However, what we saw was that this is somehow too reactive. So if your hash power plummets at some point, this strategy that I just described is going to panic and become really conservative. So what SquiRL was able to do was to recognize that when the hash power plummets, it's probably going to go back up again. And so it learns not to panic and to keep being aggressive, even when the hash power goes down. So to illustrate this, we ran SquiRL on historic data from a number of blockchains. And we assumed here that our attacker, our agent, was spending a fixed amount of fiat money on mining. Okay, so our agent puts a certain amount of money, rents a certain amount of hash power, or puts a certain amount of money into renting hash power. And over time, because of fluctuations in the participants of a particular blockchain, that relative percentage of the total hash power is also changing. Okay, so this is how we implemented this stochastically varying hash power. And what we saw is that the relative rewards of SquiRL were able to beat both the OSM strategy that I mentioned, as well as some other baselines. Okay, so the gains over OSM are pretty small. It's worth mentioning that this is like only a percentage point or two in some cases. But the point is that in situations where you have higher fluctuations, this effect is going to be more substantial. So SquiRL is allowing us to deal with a scenario where otherwise typical tools would not apply. Okay. So our second case study is to study rushing adversaries in multi-agent settings. And we didn't start out by looking at rushing adversaries. We didn't think there was a problem with the rushing adversary model. We started out by looking at a question of, is OSM and Nash equilibrium? Okay, so we wanted to understand, if you have multiple agents that are competing, is it the case that OSM is the Nash equilibrium for all of those agents? Okay, so to understand this question, we implemented 3 agents. One is honest, one uses OSM, and the third uses either deep reinforcement learning, which is this blue curve, or the third one uses also OSM, so the orange curve. So the orange curve represents 1 honest agent and 2 OSM agents, and the blue curve represents 1 honest, 1 OSM, 1 DRL. Okay. And so we wanted to understand, as the hash power of each agent increases, how does the relative reward over honest change? So this is the relative reward minus the honest guy's relative reward. So a flat line at 0 would be where you're just earning your hash power, or relative reward equal to your hash power. Now there's 2 strange things that I want to point out about this plot. The first is, why are these curves not smooth? Okay, so this looks like a bug. I don't want to go into the details of this because it's actually not very interesting. This is actually an artifact of the randomized MDP solver that was used to solve for the OSM strategy. Okay, so this is actually not anything particularly interesting. However, the second thing I want to point out actually is interesting and is kind of problematic. Why does DRL perform worse than honest? Okay, even if the DRL algorithm is using an honest strategy, it still performs worse than honest. This is very strange and also looks like a bug, but turns out is probably not. So what's going on here? To understand what's happening, we need to go back to our timing model that I described earlier. And I'm going to show you 2 sequences of events. One where the honest party mines a block, and the other where the SquiRL agent mines a block. And in this example, I'm going to assume that the SquiRL agent is using an honest policy. So SquiRL and honest are using the exact same policy. And I'm going to show you that even though they're using the same policy and have almost the same sample path, the honest party is actually getting higher rewards. Okay. So let's start. So our time step starts and the environment assigns a block to the honest guy. Honest miner now gets to take his action. He publishes and updates his state to the tip of the chain. Now the other 2 agents get to take their actions. Can adopt. So in this case, our SquiRL agent is using the honest policy. So the SquiRL agent will just adopt the longest chain. And let's suppose that the OSM agent does the same. Okay, so now everyone's at the tip of the honest chain, and the honest miner gets the block reward. Okay. Now let's see what happens if that initial block had been given to the SquiRL agent. In this case, if the SquiRL agent gets the initial block, the SquiRL agent doesn't get to take their action yet. Recall that the honest agent is the only one who gets to act in the environment. So the honest agent is going to wait because that's the correct action in this scenario. Now the SquiRL agent and the OSM agent take their actions. So the SquiRL agent is going to publish because that's the honest behavior. And the OSM agent is going to wait because he doesn't see anything to react to. Okay, so now we're in this situation. Now we need to move on to the next time step. Now in the next time step, let's suppose that the OSM agent gets a block. Once again, the honest party gets to act in the environment, and it sees it sees the yellow chain, so it updates its state to the tip of the yellow chain. And now the two agents get to act. So the SquiRL agent stays at the tip of its own chain, but the OSM agent now is going to publish its own blue block. So what do we have now? We have a fork, and this means that the OSM agent can actually win this race, whereas previously the honest agent was always winning. So this is illustrating that the OSM agent can actually take rewards away from the SquiRL agent that it cannot take away from the honest agent. Okay, so this is really explaining why, why in that previous plot, the SquiRL agent was doing worse than honest. So you might see this example and think, okay, well, this is just because you guys implemented the environment wrong or implemented the timing model wrong. But this is, first of all, this is a common modeling assumption. This is commonly done in the single agent setting. And it seems to give strange and non-physical results in the multi-agent setting. So it does seem to be a problem with modeling in the multi-agent setting. And actually we can show we can show more constrained examples of this that illustrate this problem in general in multi-agent settings with incomplete information. So to see this, consider a toy example where we have three agents who are trying to vote on one of two options. Say they're trying to vote for Bitcoin or Ethereum. And so each of our agents gets to vote for one of these. And the yellow guy's reward is equal to the maximum number of votes on any option. Okay, so notice that we have three people who are voting on two options. So one of the options is always going to have at least 2 votes. So the yellow guy's reward is always at least 2 and at most 3 if everyone votes for the same option. Okay. Now let's consider the equivalent of a rushing adversary for this toy example. The equivalent of a rushing adversary is where the honest guy's vote gets seen by the other two parties before they have to make their own vote. And now let's suppose that the blue guy employs a strategy where he always votes opposite the honest guy. Okay, so if honest guy votes Bitcoin, blue guy votes Ethereum. And notice that the blue guy and the yellow guy have to vote simultaneously. Okay, so the yellow guy voted Bitcoin and gets a reward of 2 in this case. And notice that no matter what happens, the yellow guy is always going to get a reward of 2 in this game because the blue guy is employing a strategy to vote against the honest vote. Okay. So with the rushing adversary, our expected reward is always 2. Without a rushing adversary, so where all 3 of our players have to vote exactly at the same time, there's a possibility that they'll all vote for the same thing. They might all vote for Ethereum, in which case the yellow guy gets a reward of 3. So what have we shown? We've shown here a toy example where our yellow agent's expected reward is strictly larger by using the yellow guy's reward is strictly smaller by using a rushing adversary, by having more information, which is counterintuitive and goes against the principle of a rushing adversary, which is to model a worst case adversary. So what does this mean? Well, rushing adversaries are very natural in the single agent setting, but I think we need to think a little bit more carefully about how to implement worst case adversaries in Markov games with incomplete information. And this insight, I think, is not specific to the blockchain literature. It has broader implications for the security community. But we've already seen at least one example of a published work that uses this rushing adversary in the multi-agent setting. So I think this is something that we should be aware of and think about as we try to analyze more complex multi-agent problems. Okay, so that was the second case study. Our third one is to try to understand, is selfish mining profitable in multi-agent settings? Okay, so once we fix this rushing adversary problem, once we change our model to get rid of this non-physical effect, is selfish mining profitable with multiple players? So again, recall that this is a non-stationary environment, so it cannot be solved with MDP and value iteration. And so what we did here was to train multiple SquiRL agents that compete against each other. So each experiment here has some number of SquiRL agents, and the rest of the hash power is owned by an honest agent. So here I'm showing you again relative reward minus alpha for a single agent. So the horizontal line here represents honest rewards. And what we're seeing here is really the excess reward of the agents averaged over the number of agents. So here we see that with one strategic agent, the excess reward jumps up after 0.4. And with two strategic agents, it jumps up a little bit earlier. And for those of you who are looking at this and thinking this plot looks funny, or looks incorrect, I want to point out here that this is without the rushing adversary. So the results for one strategic agent will not look the same as classical selfish mining results. And the thing that I want to highlight here is that for three strategic agents, we actually don't see any benefit at all to selfish mining for any of the hash powers that we evaluated. So again, with deep reinforcement learning, we can't prove anything, but this does seem to suggest that selfish mining may not be profitable when you have more than three competing agents. So to understand this a little bit more, just to give a little bit of intuition here, I want to show this plot, which is showing the relative reward in the solid line and the fraction of weight actions in the dotted lines. So here you can see a little peak with the dotted line. And the fraction of weight actions is like a proxy for the policy that's learned by these agents. So the more you weight, the more aggressive your agent is being. And so what we see is that here around iteration 100, this third agent decides to start weighting a lot, start being a lot more aggressive. So all three of these agents have more or less converged to honest mining. They're basically weighting 0% of the time. But then this third agent starts weighting a lot more. And all of a sudden, in response, the relative reward plunges. And this blue agent in particular is able to capitalize on that. And then they quickly settle back into honest mining. So again, this doesn't prove anything, but it does suggest, we have a conjecture that honest mining is a Nash equilibrium for k greater than or equal to 3 strategic agents. So it would be very interesting to either prove or disprove that. Currently, we don't have a good grasp on how to do that because this is a repeated game with a large state space. So it's kind of unclear. Okay, finally, I have our fourth case study, which is on attacking Casper the friendly finality gadget. So I guess we have a pretty substantial Ethereum crowd in the audience, so many of you may be familiar with this already. But for those who are not, Casper FFG is a finalization mechanism that is meant to help a chain-based consensus protocol finalize blocks. So the idea is we would like to be able to say at some point in time that block B2 is in the ledger and is never going to be removed, for example. So how does FFG work? The idea is that in addition to our regular miners who are mining blocks normally, we also have a validator pool, which is a set of nodes that put some deposit into a pool and as a result are allowed to vote in a finalization protocol. And the way this works is that at each checkpoint, so at each height in this block tree, our validators are going to vote for exactly one block at that height. So here our blue and red validators voted for B2, and our yellow validator voted for this block over here. Now, if a block manages to collect at least 2/3 of the votes of the validators, we call it justified. Okay, so the process in FFG, okay, I'm also simplifying the FFG protocol description a little bit just to make this simpler. But the protocol proceeds by having these validators justify subsequent blocks. And if we see two justified blocks that are, where one is a direct child of the other, then we say that the parent is finalized. So all of this is happening through voting, and in each case, we need to get a 2/3 supermajority on any given block that we're voting for. So how does Casper FFG protect against misbehavior? Well, the most well-known protection is that public misbehavior, i.e. equivocation, is penalized with slashing. So if the blue validator decides to vote for two separate blocks at the same height, then the blue deposit is going to get slashed. We're not going to worry about this kind of misbehavior because it's publicly visible and it's kind of easy to defend against. The second kind of protection is that if you vote on a checkpoint that's different from the justified one, your deposit gets shrunk, and the nodes that voted for the correct justified checkpoint, their deposits will grow. So for example, let's say that our yellow validator votes for B2 and our blue validator votes for this block over here. And then our red validator comes in and chooses B2. Now the blue validator voted for a block at a height that is the same as a justified block, but is not the justified block. So the blue deposit shrinks and the red and yellow deposits grow. So this is the basic incentive mechanism. And in a white paper that Vitalik posted online in 2017, they argued that each individual validator has less than, if each individual validator has less than 1/3 of the total deposit, then honest behavior is a Nash equilibrium. So what can we do with this? This has theoretical guarantees. Well, the way that we decided to structure this attack is to combine selfish mining with strategic voting. Okay? So we have agents that are both engaging in selfish mining and are also being strategic about the way that they place their votes. So an agent can choose here which blocks to build on or vote for, and it can also choose when to release blocks or votes. Okay. And once again, this state space is much too large for MDPs and policy gradient, so this would not be possible to solve with classical techniques. So when we trained SquiRL on this problem setting, it started learning the following strategy, roughly. So remember I said that our agent, in this case the red validator, is able to selfishly mine and also strategically vote. Okay, so let's suppose that our red agent has a selfishly mined red block that it's withholding. It has not published this yet. And now the rest of the participants mine a regular block and start voting for it. So the red agent is going to wait until it sees about 1/3 of the votes for, less than 1/3 of the votes for one of the blocks that's parallel to its own. Then it's going to release its withheld block and immediately vote for it. in hopes that the yellow validator will now come and join the red side. If this happens, now this red block has accumulated 2/3 of the votes, so it becomes justified. So now the blue deposit is going to shrink and the red and yellow deposits grow. So in this way, the red node is able to amplify its own fraction of the rewards in the system compared to what it should get normally. And actually, so here I'm showing you a plot of the voting reward fraction compared to the attacker's voting and mining power. So here we assume that it has equal voting and mining power. Notice that these two are measuring different quantities. So your mining power is the fraction of hash power that you own in the system, whereas your voting power is the fraction of the deposit that you put into the pool. And what's interesting here, and this light gray line, this horizontal gray line represents the 1/3 mark. So what's interesting here is that with deposits close to 0.3, you can pretty easily amplify your voting reward over 1/3. Now, this alone does not compromise the security of the voting protocol itself. However, if other validators notice that they're getting less than the expected fraction of rewards, they may drop out of the validation pool, which could actually bump agents above 1/3 of the voting power. So this could be, so this general class of attacks could be of concern if you don't choose your parameters correctly. And I think it also introduces some interesting questions about the composability of incentive mechanisms. So with that, I will wrap up. So the take-home messages that I'd like to leave you with are, first of all, that deep reinforcement learning can be a useful tool for analyzing complex incentive mechanisms, particularly when we don't have the skills or even the ability, even for a very, very skilled game theorist to analyze. In particular, it's good at dealing with situations where we have large or continuous state spaces and or non-stationary environments. So particularly when we have multiple competing agents. And by deploying SquiRL, we learned a couple of interesting things. And I think two of the most important ones are, first of all, that our classical notion of a rushing adversary seems to give counterintuitive and strange results in multi-agent games with incomplete information. And so we should probably revisit the way that we model these things as a community moving forward. And the second take-home message is that we need to think about the composability of incentive mechanisms. Just because an incentive mechanism is internally incentive compatible, it can still be the case that if you combine it with another incentive mechanism, the combination, an attacker that can exploit both of them at once may still be able to obtain disproportionate rewards. Okay, with that, I will stop talking. Thank you all for your attention, and I'll be happy to take any questions.
Thank you for that, Julia. I thought that was really interesting. I can start with the first question. So I got two, I guess. The first one's really to do with the selfish mining. The fact that if there's more than 3 selfish miners, then it should be a Nash Equilibrium, everything should work out and they're not incentivized to attack each other. Does that also hold for 2 selfish miners, or is it only 3 and above?
So we did not, okay, hang on. So let me pull up that plot again.
Oh. I guess I'm more wondering, like, if there's 2 or more selfish miners, someone's selfish mining against you, does that just disincentivize the attack altogether?
Okay, so with 2 strategic agents, we actually did observe some gains to selfish mining. So here we're assuming that these 2 strategic agents have the same, both of them have the same hash power and they're not colluding with each other. So the effect that we observed really did start with 3 agents.
I see. So for 3 agents, it is always better being honest. There's like a little bump there that shows they tried to be dishonest and it didn't work out for them.
Yeah, they did try to be dishonest. And we actually, so there's a bunch of Okay, so I think this is an important thing to mention actually for people who are interested in using these tools. DRL is super finicky. So we had to do a bunch of training tricks to get things to work. And for these experiments in particular, we were really trying to emphasize aggressive behavior. So like waiting more often. And even with that, the strategic agents did not learn to, or like every time they tried to attack one another, they lost.
Oh, okay.
So
They didn't really learn how to beat another attacker effectively.
what's that?
They couldn't work out a strategy to beat a new strategy to
Exactly.
beat the other strategy.
Exactly. Yeah.
That's quite interesting. Does anyone have any questions, by the way? You can just jump in if you want, or you can ask in the Q&A and I'll read it.
Yeah, can I ask a question?
Yeah.
I'm wondering if you've run into cases where you thought there might be additional equilibrium, so not honest, but something else. They might go there.
Great question. We did not encounter. So we had a few instances where we thought that was happening, but then they were all bugs.
Yeah, that happens.
Yeah, so we did not actually find any convincing other equilibria.
Maybe when there are a lot more agents.
Potentially. My hunch is that as you add more and more agents, honest behavior is likely to become like a stronger equilibrium. But I don't know.
Okay, it's interesting. Thank you.
Awesome. Andrew had a question as well on the Q&A. He's too shy to get off his mic, it looks like. He said, would you say it's an open question how to say something about optimality of the RL approach or to find scenarios where there are attacks out of reach of the RL?
Yeah, so, right. So this is actually a problem that's been of interest in the game theory community for a long time. So studying the multi-agent scenario in particular is a case of repeated games. And that is an active area of research right now. And we don't really have good theoretical results on it. At the same time, people are currently trying to prove things about RL algorithms, but there's very little that's known about deep reinforcement learning in particular. So we can say something about, sometimes we can say things about single agent settings, but in the multi-agent setting in particular, very little is known right now.
Awesome. I have a question about the Casper stuff. So you sort of outlined the attack, and if you're over, I got the impression if you're over 30% or more of the stake, then you can basically increase your reward disproportionately. Is there any mitigations to that? You didn't really mention if there's any way to stop that strategy or.
Yeah, great question. Okay, so we actually just got this result last week, so we're. We haven't gotten that far yet. I'm not sure. I think that timing is critical. So like the attack does rely on the fact that the honest parties are voting not all at the same time. But at the same time, forcing all of the honest parties to cast their votes at the same time is something that's not going to be possible either, just because of network delays. So it's not obvious to me at the moment how to fix it. But like I said, we haven't really known about it.
Is there any other questions in the audience? You can just yell if you want. Unmute yourself. Okay, I have one last question, and then I guess we can finish it. So this is so there's this proposal in the community called EIP 1559. I don't know if you've heard of it, but it has like two strands to it. One is that instead of paying fees, you burn fees. So if I pay, $50, the miners don't actually get the $50. It just gets burnt altogether. The second portion is that they have this gas oracle called a base fee. So if the network's congested, if the network's congested, then the base fee will go up. and that's the minimum fee anyone has to pay on the network. So if the base fee goes up, everyone has to pay $2 or more. My question is, like, do you have any insight there around, I guess, burning the fee as a mechanism compared to paying the fee? And do you think that would have any implications on like selfish mining or what the different attack strategies that the bots might do?
That's a good question. So we didn't look at transaction fees at all in this work.
Okay.
However, I think one of the things that did make the Casper FFG attack possible is the fact that if you misbehave, your deposit goes down.
Yeah.
And so like this burning of fees makes me think that like maybe there's something that could be exploited there as well.
Okay, because I mean, I'll just finish with this. They also have one really quirky thing about the protocol. So as a user, when I send a transaction, I say, this is my fee cap. I'm willing to pay up to 80 GUI. But as the base fee increases, you know, you'll get 30 GUI, 20 GUI, 40 GUI. So the reward you get per block for a transaction will decrease over time. As the base fee goes up, I'm only going to pay 80 GUI. You know, 10 gets burned, 20 gets burned, 30 gets burned. So now when you look at the transaction set, the reward isn't necessarily, you know, the transaction with the hash fee. It's the transaction with the hash fee at this block because of the fee cap.
I see.
So there's like also a little twist in the you know, how you pack transactions. And I just thought I mentioned it. Maybe something you could look at because
That's interesting. Yeah, I bet there's something that
I think there is. I don't believe that's secure. That's that I mentioned it. Okay, Veronica has one last question. What is the subtitle software that you're using?
I'm sorry.
The
Okay.
subtitle software. Everyone's amazed by it.
Yeah, I have no idea. My PowerPoint just started doing it.
There you go, Veronica. It's PowerPoint.
I guess update your Microsoft Office. I don't know.
That's awesome, then. There you go, guys. Because I had a few pings after you started speaking, and they said, "What subtitle software is she using?"
I have no idea.
Awesome. Okay, thank you for that, Julia. Anyway, thank you for the talk. I thought it was really interesting. I think lots of other people did as well.